Tonight we are going to ask one of the oldest questions humans have ever asked, but we are going to ask it carefully. Not, do aliens exist? Something narrower. Will we ever, in any future we can credibly imagine, actually detect them? The difference between those two questions is much larger than it sounds. We could share the galaxy with 1 million civilizations and never see a single one. We could be entirely alone and never be sure. Pull up the covers. We will now walk through the strangest gap in modern astronomy. The space between knowing life is probably out there and being able to point at one specific case and prove it. And the closer you look at that gap, the stranger it turns out to be. Part 1. The Signal We Cannot Ignore. On the 17th of April, 2025, a small team at the University of Cambridge stood in front of the world's press and said something that, for about 10 days, made every other story stop. They said they had found a molecule in the atmosphere of a planet 124 light-years away that on our own planet is made almost entirely by living things. The molecule was called dimethyl sulfide. The planet was called K2-18b. And the question that had been hovering quietly behind every human telescope for more than half a century suddenly walked into the room. Have we just found alien life? The team did not say yes. They were careful. They said the detection was at 3 sigma, which means the chance of the signal being random noise was about 3 in 1,000. They said it was suggestive. They said it was the strongest hint anyone had ever obtained from another world. They used the words possible and tentative almost as often as they used the word detection. But the press and the public and the algorithm that decides what trends did not hear those qualifiers. The headline that travelled around the planet in the next 48 hours was simpler. Scientists have found signs of life on K2-18b. And then, slowly, over the following months, the detection unravelled. Other teams reanalyzed the same data from the James Webb Space Telescope and came to different conclusions. One paper, by researchers at Arizona State, found that the signal was consistent with what they called a flat line, meaning it might not be a signal at all. Another paper, filed at RxIve as preprint 250 4.12267, used additional infrared data from a different instrument on the same telescope and concluded that the dimethyl sulfide detection did not survive. A third paper showed that the choice of atmospheric model could produce or erase the signal from exactly the same underlying numbers. By the end of 2025, the only honest summary of the K2-18b story was this. We have a remarkable piece of data, gathered with the most powerful telescope ever built, pointed at one of the most carefully studied planets we have ever found, and we cannot tell you whether it means there are aliens. I want you to sit with that for a moment, not because it is dramatic, because it is the truth of where we are, the most powerful telescope in human history, the most carefully studied exoplanet ever discovered. 150 hours of observation time, which is an almost unimaginable amount when you consider how many other things the world's astronomers wanted to look at. And the answer, after all of that, is we still don't know. This is the question I want to walk through with you tonight. Not whether aliens exist, we will get to that, but something narrower and in some ways more interesting. Will we ever detect them? Will we ever, in any future we can credibly imagine, point an instrument at the sky or at the soil of another world and produce evidence that is good enough, clean enough, certain enough to say, with confidence, that there is a second life out there? The K2-18b episode is not an embarrassment, it is a preview. It is the shape of every detection we are likely to make for the rest of this century and possibly the rest of human history. So settle in, take whatever long breath you take before you put your head on the pillow, We are going to walk together through 3 frontiers tonight, slowly, the way you might walk through a museum after closing time, when there is no one to hurry you. The first frontier is the atmosphere of distant planets, where we use the absorption of starlight to read the air of worlds we will never visit. The second frontier is the radio signal, where we listen for the kind of message a civilization might leave even when it does not mean to. The third frontier is the ocean, the closer one, the moons of Jupiter and Saturn, and the soils of Mars, where we might actually pick something up in our hands and turn it over in a laboratory. And running through all 3 is one quiet question. Why has every single one of these searches produced exactly the same kind of result? Not nothing, not certainty, something in between, something I want to call the gap. The gap is the distance between possibility and proof. It is the place where the data hovers and the experts argue and the public moves on and the next observation is scheduled. Most of the time, when we talk about scientific discovery, we imagine a clean moment. A telescope swings, a light blinks, a paper is published, and the world knows something it did not know before. The discovery of life beyond Earth is almost certainly not going to be like that. It is going to look more like K2-18b, months of careful work, a tentative detection, a counterpaper, a working group, another year of observation, a revised statistical confidence. A press conference that begins with the words, "We are pleased to announce," and ends with the words, "More work is needed." I want to be honest with you about something else. There are 2 ways this search can fail. The first is that we miss it. Real life is out there, and our instruments are not sensitive enough, our methods are not clever enough, our chemistry is not flexible enough, and we walk past it. The second is that we declare it, and we are wrong. We get the signal we have been waiting for, and the human story changes for a week, and then a quiet team in a quiet building finds the satellite, or the microwave oven, or the chemical artifact that explains everything, and we slip back into the silence. Both of these failures have happened before. Both of them are still happening. The pattern of detection in this field has been, for 65 years, a slow oscillation between hope and explanation, and the oscillation has not slowed down. The names that will come up tonight are worth holding lightly in your mind. Frank Drake, who pointed the first telescope at the right star and listened for the right reason. Carl Sagan, who taught the world to think that the cosmos was a personal question. Jill Tarter, who ran the search for 30 years and never heard the signal. Enrico Fermi, who asked the simplest possible question in front of his lunchmates and changed the field forever. Niku Madhusudan, who pushed harder than anyone has pushed on a single planet. Avi Loeb, who keeps insisting that we are not asking strange enough questions. Each of these people has a moment in the story that follows. None of them, yet, has heard back. There is another piece of context worth laying down before we move. The K2-18b episode was not an isolated event. It sits inside a longer sequence of similar episodes that have been arriving every few years for almost 2 decades now. The phosphine detection at Venus by Jane Greaves and her team in 2020 followed exactly the same trajectory. Strong initial claim, worldwide press attention, follow-up papers, partial withdrawal, a long, quiet argument that never quite resolves. The Mars methane mystery, where the Curiosity rover detected small bursts of methane in Gale Crater that the ExoMars Trace Gas Orbiter has been unable to confirm from above, has the same shape. Even the original Viking lander experiments in 1976, which produced positive signals on one of 3 life detection tests and contradictory signals on the others, have been argued about for 50 years without resolution. The pattern is older than the equipment. By the end of this episode, you will know exactly why the question in our title cannot be answered with a confident yes or a confident no. You will also know why that uncertainty, which sounds at first like a failure of our methods, may turn out to be the answer itself. The detection of alien life, if it ever happens, will probably not look like the moment in a science fiction movie. It will look like a quiet argument that lasts longer than any of us. And the more time you spend with the actual evidence, the spectra, the candidates, the rocks, the moons, the more you start to suspect that the gap between possibility and proof is not a temporary problem. It is the shape of being a young, listening species on a small planet in a galaxy too big to canvass. So let us begin, slowly, with the long history of looking. Is less than break time equals 1s. Is greater than number. Part 2. A short history of looking. The first deliberate search for an alien signal began on a cold morning in April of 1960 at a radio observatory in Green Bank, West Virginia. A young astronomer named Frank Drake pointed a 26-meter dish at a star called Tau Ceti, 11.9 light-years away, and started listening. He had chosen his frequency carefully. He listened at 1,420 megahertz, the natural radio frequency of neutral hydrogen, the most abundant element in the universe. If a civilization wanted to be found, Drake reasoned, this was the frequency they would broadcast on. It was the one frequency every astronomer in the galaxy would already be paying attention to. He listened for 6 hours that first day. He heard nothing. He aimed the dish at a second star, Epsilon Eridani, 10.5 light-years away. He listened there for another 6 hours. Halfway through the second observation, the receiver picked up a strong narrowband pulse. Drake said later that he froze in place. He repointed the antenna away from the star. The signal continued. He repointed back. The signal was still there. It turned out to be a passing military aircraft, a high-altitude experiment of some kind, broadcasting on a frequency it should not have been on. Project Ozma, as the experiment was called, ran for about 200 hours over 4 months. It detected nothing real. Drake, who was 29 years old at the time, did not consider the result a disappointment. He had proven that the technology worked. He had proven that the methodology was sound. He had proven that you could, with serious astronomical equipment, deliberately and rationally search the sky for the signature of another civilization, and that the equipment could tell you the difference between a real signal and a piece of human interference. Even if every time he did it, he found human interference. In the autumn of 1961, Drake organized a small meeting at Green Bank. He invited about a dozen scientists, including Carl Sagan, who was then a junior researcher at Yerkes Observatory. He wrote an equation on the chalkboard in the front of the room that would later carry his name, the Drake equation. The number of detectable civilizations in our galaxy equals the rate of star formation, multiplied by the fraction of stars with planets, multiplied by the number of habitable planets per star, multiplied by the fraction of those that develop life, multiplied by the fraction of those that develop intelligence, multiplied by the fraction of those that develop communication technology, multiplied by the length of time such a civilization remains detectable. It is not really an equation. It is a way of organizing your ignorance. The first 3 terms are now reasonably well known because we can count stars and we can count exoplanets. We know that stars form at roughly 1 to 3 per year in the Milky Way. We know that almost every star has at least one planet. We know that something like 1 in 5 sun-like stars has a roughly Earth-sized planet in the habitable zone. But the last 4 terms, the ones that actually decide whether the galaxy is full or empty, are not known at all. We have one data point for them, us, and one data point is not enough to do statistics with. Then came the wow signal. On the night of August 15th, 1977, at the Big Ear Radio Telescope at Ohio State University, the receiver picked up a narrowband signal that was 30 times stronger than the background noise. The telescope was fixed. It did not move. The sky rotated past it. The signal lasted exactly 72 seconds, which is the length of time a single point in the sky took to drift across the beam. It was at 1,420 megahertz, the same hydrogen line Drake had chosen 17 years earlier. It had every property a real interstellar signal should have. 3 days later, a graduate student named Jerry Eman was reviewing the printout from that night's observation. He saw a column of intensity values that read, in his telescope's encoding, 6EQUJ5. He circled it in red ink. In the margin, he wrote a single word, "Wow, the signal has never recurred." The Big Ear has been retrained on that patch of sky hundreds of times in the 49 years since. Other telescopes have looked too. Nothing. The current best mainstream explanation is that 2 passing comets, named 266P/Christensen and 335P/Gibbs, happened to be in the right place at the right time and emitted unusual hydrogen line radiation, though even this explanation has its critics. For 1 minute and 12 seconds, on a hot August night in Ohio, the universe seemed to whisper, and then it stopped, and it never whispered again. In 1974, 3 years before the WOW signal, Frank Drake and Carl Sagan composed a message of their own. They aimed it at M13, a globular cluster of about 300,000 stars, 25,000 light-years away. The message was encoded as a binary picture, a stylized human figure, a graphic of DNA, a diagram of the solar system, a representation of the Arecibo telescope itself. It took 3 minutes to transmit. The earliest possible reply, assuming someone heard it and immediately answered, would arrive in approximately 50,000 years. By then, no one alive today will be alive. By then, the configuration of M13 will have changed, and the stars Drake aimed at will no longer be where they were when he aimed. This is the timescale of the question. This is what it means to make contact across interstellar distances. A single conversation, one statement and one reply requires longer than the entire history of agriculture. The pioneer plaques came earlier, in 1972 and 1973. 2 small gold anodized aluminum plates were bolted to the Pioneer 10 and Pioneer 11 spacecraft, with diagrams of a man and a woman, a pulsar map showing the solar system's location, and the same hydrogen line frequency Drake had listened on. The Voyager Golden Records, launched in 1977, carried more greetings in 55 languages, the sounds of whales and storms and human heartbeats, music from Beethoven and Chuck Berry. Both spacecraft are now beyond the heliopause, in true interstellar space. Pioneer 10 is silent. Voyager 1 is fading. We threw 4 small objects out of the solar system without any actual plan for what we would do if someone found them. And underneath all of this, underneath 65 years of Drake equations and WOW, signals and golden records, the same pattern keeps repeating. Every era of looking produces one, almost. Ozma's silence. Wow, 72 seconds. The Tabby's starlight dips. The BLC-1 candidate. Then a long period of follow-up, a slow re-explanation, and a return to listening. We have been on the edge of certainty for half a century, and the edge has not moved. The frequency of the candidates has gone up, the quality of the data has gone up, the number of telescopes has gone up, the result is the same. A flurry of suggestive observations, a period of careful argument, a quiet return to the catalogue of unresolved cases. There is now an entire informal subdiscipline of astronomy dedicated to revisiting old SETI candidates and explaining them with new physics. It is a strange kind of forensic astronomy, working backward from the original announcement to the mundane source. The question, when you stand inside it, is whether this pattern is a feature of our methods or a feature of the universe. We will not be able to answer that question tonight, but we can walk closer to it. Is less than break time equals 1s, is greater than number, part 3, the Fermi paradox and the Great Silence. Some years before any of this, before Drake, before Sagan, before the Big Ear and the Arecibo message, a much simpler question was asked in front of 3 other physicists during a walk to lunch. It was the summer of 1950 at the Los Alamos National Laboratory in New Mexico. The 4 men were Enrico Fermi, who had built the world's first nuclear reactor, Emil Konopinski, Edward Teller, who would help build the hydrogen bomb, and Herbert York. They were walking from their offices to a cafeteria called Fuller Lodge. They had been talking about a recent New Yorker cartoon which showed an alien wandering through Manhattan with a trash can, ostensibly explaining the recent disappearance of public refuse bins around the city. The conversation drifted into idle speculation about whether intelligent life was common in the galaxy and how fast such life could spread. Fermi did some quick mental arithmetic. He thought about the number of stars in the Milky Way, the age of the galaxy, the speed of plausible interstellar travel. Halfway through the meal, he stopped, looked at his companions, and asked one of the most quoted questions in modern physics. But where is everybody? The math, in the version we use now, goes like this. The Milky Way is about 13 billion years old. There are between 100 and 400 billion stars in it. At least 1 in 5 sun-like stars hosts a roughly Earth-sized planet in the habitable zone. Even a civilization that traveled at only 1% the speed of light, which is 1,000 times slower than the speed limit of the universe, and well within what we can already imagine technologically, could cross the entire galaxy in about 10 million years. Compared to the age of the galaxy, 10 million years is essentially nothing. It is the last 1/10 of 1% of cosmic time, and it gets worse. In 1953, the mathematician John von Neumann was working on the theory of self-replicating machines. He showed that a single probe, built to reproduce itself from raw materials, could fill an entire galaxy with copies in a startlingly short time. You launch 1 probe. It travels to the nearest stellar system. It mines the asteroids there for metal. It builds 2 more probes. They fly to 2 new stars. They each build 2 more. After fewer than 50 doublings, the entire galaxy is colonized by your probes. Even if each probe travels slowly, the total time is measured in tens of millions of years, not billions. So here is the puzzle. If even one civilization in the history of the galaxy decided to build probes, the entire galaxy should be full of them by now. We look up, we see stars, we see planets, we see beautiful structure. We do not see probes. We do not see megastructures. We do not see deliberately altered stellar systems. We see what looks like an untouched cosmic neighborhood, billions of years old, completely empty. In 1998, an economist named Robin Hanson wrote a short paper that gave this puzzle a name. He called it the Great Filter. Somewhere on the path from no life to galaxy-spanning civilization, there must be at least one step that is almost impossibly hard. So hard that almost no civilization makes it through. The question is whether that step is behind us or ahead of us. If the filter is behind us, the answer is comforting in one way and lonely in another. Maybe the origin of life itself is rare. Maybe the transition from simple cells to complex cells took such an unlikely chemical accident that it has not happened anywhere else in the galaxy. Maybe intelligence is rare, or technology is rare. In this version of the story, we are alone, but we are also safe. We have already passed whatever was going to kill us. If the filter is in front of us, the answer is much more uncomfortable. It means civilizations regularly arise and regularly destroy themselves before they can leave a mark on the galaxy, maybe by nuclear war, maybe by climate collapse, maybe by something we have not yet invented. In this version, the silence is a warning. Every star in the night sky is the grave of a civilization that did not make it. There is a third possibility worth holding on to, which is that the filter is neither behind us nor in front of us, but distributed. Maybe every step on the path from chemistry to civilization is moderately unlikely, and the compounding of those moderate unlikelihoods produces the silence we observe. The origin of life, the eukaryotic transition, the emergence of multicellular organisms, the development of language, the survival of nuclear-armed civilizations through their first century of nuclear weapons. Each of these may be plausible but not certain. Multiply enough plausible but uncertain steps together, and you get a galaxy that is almost empty, even though no single step was impossible. This is the version of the Great Filter that working biologists tend to find most credible. It is also the least dramatic, which is probably why it does not get talked about much. There is also a quieter version of the paradox that does not require any filter at all. Maybe civilizations stop colonizing space, not because they die, but because they stop wanting to. Maybe after a certain technological threshold, expanding into matter becomes less interesting than expanding into information. Maybe most civilizations turn inward, build their own simulated universes, and lose interest in occupying the real one. The result, from our point of view, is the same, an empty galaxy. But the reason is not extinction. The reason is preference. Most people who think hard about the Fermi paradox have come to a difficult conclusion. The silence does mean something. It is one of the most informative observations astronomy has ever made. The galaxy, by all rights, should be full. It is not. That fact alone, the simple, negative observation of nothing, narrows the possible answers in ways we are only beginning to understand. There is one more wrinkle worth holding on to before we leave the Fermi paradox behind. The version of the paradox most people encounter assumes that detectable civilizations would naturally leak signs of their existence, radio emissions, infrared waste heat, modified stellar systems. But this assumption is itself a guess about how technological civilizations behave. We have one example, ourselves, and we are only about 120 years into our radio-emitting phase. Our own peak radio leakage may already be behind us. As fiber optics, cellular networks, and lower-power digital communications replace high-power broadcast television and radio, the amount of energy Earth dumps into space at narrowband frequencies is actually dropping. If our future trajectory is typical of technological societies, then the average civilization may only be detectable by SETI for a window of a few hundred years before becoming dark again. Multiply that by the rarity of overlap in time, civilizations would have to be transmitting in the same century we are listening, and the apparent silence stops being surprising. It becomes the expected result. This is a version of the Drake equation where the last term, the lifetime of detectable civilizations, may be much smaller than people originally hoped. The galaxy may be full of life. The galaxy may even be full of intelligence. The number of intelligences detectable by our specific methods at our specific moment in time may still be very small, maybe zero. We could be alone in our era without being alone in the universe at all. This is the place where the central thread of tonight bends back on itself. The question of detection is not just a question of building better telescopes, it is a question of what we should expect to find when we point them up. The Great Silence is, in a strange way, the largest single detection humans have ever made. We have detected the absence of detectable civilizations within at least a few hundred light-years of Earth, across at least all the wavelengths we have been able to monitor for several decades. That is data. It is not the data we wanted, but it is data, and the rest of tonight is going to be about trying to figure out what that data means. Is less than break time equals 1s is greater than number. Part 4. How to read a planet from 100 light-years away. Let me try to explain, slowly, what it actually means to read the atmosphere of a planet we cannot visit. Because the technique is so improbable, so close to magic, that it is worth pausing on, even if you have heard about it before. Step back for a moment and consider how unlikely this whole project would have seemed to anyone living 100 years ago. In 1925, the idea that we could detect chemistry in the atmosphere of a planet circling another star would have been treated as fantasy. We had not yet confirmed that other galaxies existed. The first exoplanet around a Sun-like star, 51 Pegasi b, would not be discovered until 1995, exactly 30 years before the K2-18b announcement. The leap from "we suspect planets exist around other stars" to "we are reading the air of those planets" took place inside a single human lifetime. That progress is, by any reasonable standard, miraculous. The fact that we cannot quite reach certainty yet is not because the project is hopeless. It is because the project is hard, and we are still very early in it. A planet orbiting another star is, for most of its orbit, completely invisible to us. The star is roughly 1 billion times brighter than the planet that goes around it. Trying to see the planet directly is like trying to see a firefly next to a lighthouse. For most planets we have detected, we have never actually seen them. We have only seen the way they affect the star they orbit. But once in a while, a planet, on its journey around its star, passes directly in front of the star from our point of view. We call this a transit. From our perspective, the star gets a tiny bit dimmer for a few hours, as the planet's silhouette blocks a small fraction of the light. For an Earth-sized planet around a Sun-sized star, the dimming is about 1 part in 10,000. For a larger planet around a smaller red dwarf, the dimming can be as much as 1 or 2%. Now here is where it gets clever. During the transit, a small fraction of the starlight does not just get blocked. It passes through the upper atmosphere of the planet before continuing on to us. The atmosphere is thin, but it is there, and the molecules in that atmosphere absorb specific wavelengths of light. Water absorbs at 1.4 microns. Methane absorbs at 3.3 microns. Carbon dioxide absorbs at 4.3 microns. Each gas writes its own fingerprint in dark lines across the spectrum of the starlight that filters through. When the planet is in transit, you compare the spectrum of the star to the spectrum of the star without the planet in front of it. The difference, after enormous care and an enormous amount of data, is the spectrum of the planet's atmosphere. You are not looking at the planet. You are looking at the starlight that touched it for a moment. The James Webb Space Telescope, which launched on Christmas Day 2021, is the first telescope sensitive enough to do this kind of measurement on small, cool planets. Its primary mirror is 6.5 meters across, made of 18 hexagonal segments of gold-plated beryllium. It sits at a place called the second Lagrange point, about 1 million miles from Earth, where the gravity of the Sun and the Earth combine to hold it in a stable orbit. It is permanently cooled to about minus 223 degrees Celsius. That cold is not a luxury, it is a requirement. JWST is looking for infrared light, and any warm object, including the telescope itself, would glow at infrared wavelengths and drown out the signals it is trying to read. The sunshield that keeps the telescope cold is itself one of the marvels of the mission. It is the size of a tennis court. It is made of 5 layers of a polymer film called Kapton, each layer only thousandths of a millimeter thick, coated with aluminum and silicon. The sunshield reduces the heat reaching the telescope by a factor of about 1 million. Without that engineering, JWST could not exist. The entire enterprise of exoplanet atmospheric spectroscopy at small worlds depends on a piece of foil being unfolded correctly in the dark, 1 million miles from Earth, in 2022, with no possibility of repair if anything goes wrong. The unfolding took 2 weeks. It worked. A single observation of a planetary atmosphere using JWST takes between 20 and 40 hours of telescope time. To get statistical significance, You usually need to observe several transits in a row. K218. B has now consumed more than 150 hours of JWST observation, which makes it the most expensive single exoplanet target in the history of astronomy. The numbers you can extract from this kind of work are almost ridiculous. With a single 30-hour observation, you can detect specific molecules at concentrations of a few parts per million across an atmosphere on a planet so far away that its light has been traveling toward us since the late 1800s. Astronomy, as a practical craft, has reached a level where it is doing chemistry on objects we will never touch. But the limits are equally important to understand. The signal sits right at the edge of the noise. To get from "we see a hint" to "we are certain," you sometimes need more observation time than the entire mission can afford. The noise sources are everywhere. Cosmic rays hitting the detector, tiny temperature fluctuations in the spacecraft, variability of the parent star itself, which is often more active than our own Sunday. Even the way you stack and process the data introduces choices that can produce different results from the same raw bytes. Red dwarfs in particular are a problem. They are flare stars. They erupt unpredictably, sometimes producing bursts of ultraviolet and X-ray radiation that can dwarf their normal output for hours. K2-18, the host star of K218b, is one of these. The flares change the background spectrum the planet's atmosphere is imprinted on. If a flare happens during one of your transit observations, and you do not correctly model its effect, you can produce a spectral signature that has nothing to do with the planet at all. Disentangling stellar variability from planetary chemistry is one of the hardest problems in modern exoplanet science, and it is far from solved. This is where statistical confidence enters. In physics, we talk about sigma values, which measure how many standard deviations a signal is above the background. 1 sigma is 68% confidence. 2 sigma is 95%. 3 sigma is 99.7%. 5 sigma is the discovery threshold for particle physics, and it means about 99.99999, 4% confidence, about 1 chance in 3.5 million that the signal is random fluctuation. Most exoplanet biosignature claims live in the 3 to 4 sigma range, which means they are interesting but not conclusive. They might be real. They might be statistical artifacts. The data does not always tell you. There is one more thing you have to understand about this technique, and it is the most uncomfortable thing. A signal can be exactly the thing you predicted, exactly the molecule you were hoping for, exactly the spectral shape that life on Earth would produce, and still be wrong. Because for almost every biosignature gas you can imagine, there is at least one non-biological way to make it. The chemistry of dead worlds is surprisingly creative. We will get to that in detail. For now, hold this thought. With the most powerful telescope in human history pointed at one of the most habitable-looking planets we have ever found, with more observation time than almost any other target has ever received, we still cannot answer the question, why not? That is what the next part is about. The answer is going to be uncomfortable, because it is going to be partly about chemistry and partly about how science gets argued in public, and the two things are not the same thing. Is less than break time equals 1s is greater than number, part 5, K218b, and the DMS controversy. K218b was discovered in 2015 by the Kepler Space Telescope during its extended K2 mission. The planet is what astronomers call a sub-Neptune. It is 8.6 times the mass of Earth, 2.6 times the radius. It orbits a red dwarf star, a small, cool, long-lived star, much less bright than our Sun once every 33 days. Its star, K2-18, sits 124 light-years away in the constellation Leo. When the planet was first found, no one paid it much attention. There are now more than 6,000 confirmed exoplanets in the catalogue, and K2-18b was just one more entry. It became interesting when astronomers realized two things. First, it sits inside the habitable zone of its star, where temperatures should allow liquid water on the surface, if there is a surface. Second, it might not have a surface in the traditional sense. It might be a Haitian world. The Haitian hypothesis was proposed by Niku Madhusudan and his team at Cambridge in 2021. The word is a combination of hydrogen and ocean. A Haitian world would be a planet with an atmosphere mostly made of hydrogen, sitting on top of an ocean of liquid water hundreds of kilometers thick. Such a world would be very different from Earth. The surface gravity would be different. The pressure at the ocean floor would be enormous. The light from the parent star would filter down through clouds and an enormous depth of water before reaching anything that lived there. But the chemistry would, in principle, be hospitable. And this was the key insight. The atmosphere of a Haitian world would be relatively easy to study with JWST, because hydrogen-dominated atmospheres are puffy and produce strong spectral signals. K2-18b became the prototype Haitian planet. JWST observations began in 2023. The first results, published that September by Madhusudan and his colleagues, detected carbon dioxide and methane in the planet's atmosphere. The two molecules together hinted, faintly, at a third dimethyl sulfide, the molecule that on Earth is made overwhelmingly by marine phytoplankton in our oceans. The signal was weak. The team published carefully. They said the detection was tentative. They said more observations were needed. More observations came. On the 17th of April, 2025, the team announced a second result. The dimethyl sulfide signal was still there, and now there was a hint of a related sulfur molecule called dimethyl disulfide as well. Both of these compounds, on Earth, are produced overwhelmingly by biological processes. There is no major non-biological source of either molecule that has been demonstrated in laboratory experiments at the scale required to produce the K2-18b signal. The team's statistical confidence was 3 sigma, about 99.7%. The press release used the phrase, "the most promising signs to date of a possible biosignature beyond our solar system." Madhusudan, who is a careful and measured scientist, told reporters that he was confident the team would have a stronger result within 1 to 2 years. Other astronomers, watching from the sidelines, were less certain. A 3 sigma signal, in this field, has often turned out to be wrong. The phosphine detection at Venus, 4 years earlier, had been at a similar level of statistical confidence and had largely been walked back by the time of the K2-18b announcement. 3 sigma is the kind of number that makes a scientist excited and makes a careful editor cautious. Within 2 weeks, the first rebuttal arrived. A team, led by Luis Wellbanks at Arizona State University, took the same JWST data and reanalyzed it with a different set of atmospheric models. They reported that the dimethyl sulfide signal, when subjected to a wider set of model assumptions, was consistent with what they called a flat line, meaning that within the noise of the measurement, the signal might not be a signal at all. Within a month, another paper appeared on the RCEIV preprint server with the identification number 250-4.1-2267. The authors, led by Andrea Pica Chiamara at the University of Cambridge, yes, the same Cambridge, working on the same planet, with different conclusions, had analysed additional infrared observations of K2-18b taken with the MIRI instrument on JWST. Their analysis did not support the dimethyl sulfide detection. They concluded that the strongest signal in the data could be explained by other, more conventional molecules. A third team, in late 2025, raised a separate issue. They showed that the K2-18b spectrum was unusually sensitive to the choice of atmospheric model. If you assumed the planet was a Haitian world, You got one set of molecular detections. If you assumed it was a mini Neptune with a small rocky core, you got another. The data, by itself, did not distinguish strongly between the two models. The argument is still going on. There will be more observations of K2-18b, more papers, probably another announcement, probably another rebuttal, probably another round of refining the statistics. The current consensus, as of right now, is that K2-18b is the most studied exoplanet in human history, and we cannot tell you whether there is life in its atmosphere. I want to be very precise about why this matters. It is not because K2-18b is a failure of method. The method is fine. The telescope is fine. The team is excellent. The problem is that the universe, when you ask it a question this hard, does not always answer cleanly. The signal exists. The interpretation does not. We are not stuck because we lack data. We are stuck because the data is genuinely ambiguous in a way that no amount of additional observation may resolve. There is something almost poetic about the fact that K2-18b is the planet where this conversation became public. Madhusudhan and his team are not careless researchers. They are among the most careful exoplanet atmosphere modelers in the world. The Cambridge group does the kind of slow, methodical, statistical work that other teams build their methods on. The dispute is not between competent and incompetent researchers. The dispute is between several competent groups looking at the same data and producing different answers because the data does not fully constrain the answer. This is what real science at the frontier of a hard problem looks like. It is not the tidy story of the textbook. It is people arguing in good faith for a long time about what a number means. This is the gap. This is the actual experience of detection, as it exists today, at the level of the working scientist. You have a candidate. You have a careful analysis. You have a tentative detection. And then you have a year of arguments, and at the end of the year, you have a new tentative detection that is, if anything, less certain than the one you started with. The gap is not a temporary state. It is the place where the question lives. There is something else worth noting here, because it bears on the central question. The K2-18b story has been treated, in the press and in the public, as if it were a binary. Either there is life there, or there is not. That framing is wrong. What we have is a probability distribution. We have, depending on which paper you trust, maybe a 30% chance the signal is real and biological, maybe a 30% chance it is real and non-biological, maybe a 40% chance it is noise. Numbers in those ranges are roughly consistent with where the field has landed after a year of fighting. And the truth is that distribution may not shrink much, no matter how much more data we collect. The molecules we are looking at have non-biological pathways. The star is an active red dwarf, which makes everything harder. The signal is at the limit of what JWST can do. There is one detail about the K2-18 system that often gets lost in the public version of the story, and that is worth pulling forward. K2-18b is not in an ideal orbit. It receives roughly the same amount of stellar energy as Earth does, on average, but it gets that energy from a red dwarf, which means most of the radiation arrives at longer wavelengths, with intermittent ultraviolet flares mixed in. The planet's chemistry, if there is biology in its atmosphere or its hypothetical ocean, would be operating on a substantially different rhythm from Earth's. The exoplanet that captured the world's attention in 2025 is, by Earth standards, an extremely strange place. If life exists there, it would be life of a kind we have never seen, breathing chemistry we have never tested. The fact that we cannot interpret its atmospheric signals cleanly may not be a defect of our instruments. It may be that we are looking at a kind of biology, if it exists, that our intuitions are not yet trained for. We are not going to know, not soon, maybe not ever, for this particular planet. The next planet, the one after that, the 25 worlds that the Habitable Worlds Observatory hopes to image in the 2040s, they will all live in the same gap. We will get better at narrowing it. We may never close it. Is less than break time equals 1s is greater than number, part 6. The Biosignature Problem. This brings us, naturally, to a deeper question. What does a biosignature actually mean? We have used the word casually, the way it gets used in news articles. But the definition matters because the whole search depends on it. A biosignature is any pattern, chemical, physical, geological, that is best explained by the presence of life. The word best is doing a lot of work in that definition. Because for almost every candidate biosignature we have ever identified, there is at least one non-biological explanation. The history of biosignature science is, in large part, the history of finding those alternative explanations. The classical biosignature is the pair of oxygen and methane in disequilibrium. On Earth, the atmosphere is about 21% oxygen and about 1.5 parts per million methane. These two gases should react with each other quickly. Methane plus oxygen produces carbon dioxide and water. The reaction is fast on chemical timescales. The fact that both gases exist together in our atmosphere, year after year, century after century, means that something is producing them continuously. On Earth, that something is life. Photosynthesis pumps out oxygen. Microorganisms in wetlands and the guts of animals pump out methane. The pair, together, in the right ratios, is the strongest atmospheric biosignature we currently know how to look for. The catch is that there are abiotic ways to produce oxygen. The most important is photolysis. When ultraviolet light from a star hits water vapor in the upper atmosphere of a planet, it can break the water molecule apart into hydrogen and oxygen. The hydrogen is light enough to escape into space. The oxygen, being heavier, hangs around. If the process runs for long enough, you can build up a substantial oxygen atmosphere on a completely dead world. Venus may have done this when it was younger. Some exoplanets in tight orbits around very active stars almost certainly do this. Methane has its own abiotic pathways. The most important is serpentinization, which is the hydrothermal reaction between water and certain iron, and magnesium-bearing rocks called olivines. When water seeps into ocean floor rocks and the temperature is high enough, the chemistry produces methane and hydrogen as natural byproducts. On Earth, serpentinization happens at mid-ocean ridges. On Enceladus and Europa, where we have evidence of subsurface oceans in contact with rock, it is probably happening too. Methane on an icy moon does not, by itself, imply life. The history of the abiotic oxygen idea is itself instructive. For decades, atmospheric scientists assumed that detecting molecular oxygen on an exoplanet would basically settle the question of life. Oxygen was thought to be biologically generated almost everywhere it could be measured. Then a series of theoretical papers in the 2010s by Robin Wordsworth at Harvard and others showed that there were entire categories of planets' water worlds around active stars, hydrogen-poor planets, in certain orbital configurations where oxygen could build up without any biology at all. The biosignature, that was supposed to be the slam dunk, turned out to require additional context to interpret. The slam dunk became a free throw. The free throw turned out to depend on the player. The metaphors keep failing because the science keeps getting harder. Other candidate biosignatures have similar problems. Ozone is mostly produced from oxygen by ultraviolet light, so it inherits all of oxygen's false positive issues. Nitrous oxide, also called laughing gas, is produced by life on Earth, but also by lightning and by certain volcanic processes. Phosphine, famously detected on Venus in 2020 by a team led by Jane Greaves, was at first interpreted as a potential biosignature, then partially walked back when other groups failed to reproduce the result, then linked to possible volcanic chemistry. The Venus phosphine story is, in some ways, the small precursor of the K2-18b story. So the question becomes, what would actually convince us that life had been detected? The honest answer is that we do not have a single biosignature observed in isolation that would do it. What we would need is a constellation of signals, oxygen and methane together in disequilibrium, plus the right kind of nitrogen chemistry, plus a planet in the habitable zone of a star that does not seem capable of producing those gases by photolysis alone, plus, ideally, a seasonal modulation, the kind of variability you would expect if a biosphere was breathing in and out as the planet's seasons changed. The criteria, taken together, are stringent. They are also in some sense calibrated for Earth. And this brings us to the most uncomfortable part of the biosignature problem, which is the shadow biosphere idea. The phrase was coined by Paul Davies at Arizona State, and the idea, in its starkest form, is this. Life on Earth as we know it may not be the only life that has ever arisen on Earth. There may be a second, independent origin, a tree of microorganisms that uses different amino acids, a different genetic alphabet, different metabolisms that exists right now in some hot spring, in some buried aquifer, in some patch of ocean sediment, and that we have not noticed. We have not noticed because all of our microbial detection methods are calibrated for our own kind of life. We look for DNA, we look for ribosomes, we look for specific lipids. A shadow biosphere, by definition, would use none of those, or different versions of those. Our entire microbiology is built around recognizing relatives, not strangers. If a second tree of life might exist on our own planet, undetected, what hope do we have of detecting one 100 light-years away with an absorption spectrum? We are calibrating our distant search for the only kind of life we know. If alien life uses different chemistry, we may simply walk past it. There is also the reverse problem, which is anthropomorphism in our biosignature choice. We assume aliens will produce gases similar to what life on Earth produces. But the dominant biology on Earth was anaerobic for nearly 2 billion years. From the origin of life around 3.8 billion years ago to the Great Oxidation Event around 2.4 billion years ago, life on Earth produced almost no atmospheric oxygen. Microbes in those eras produced sulfides, methane, traces of other reduced gases. From 100 light-years away, an alien astronomer pointed at our planet during that era would have seen no oxygen, no clear biosignature, and would have walked away saying, "Interesting world, probably no life." That alien astronomer would have been wrong. Earth was teeming with life, just not the kind that breathes our chemistry. The implication is staggering. The bulk of Earth's biological history was undetectable by the methods we are now using to look at exoplanets. Most of the time life has existed on our own planet, it would have failed our own detection tests. Why would we expect to do better on someone else's world? The shadow biosphere question is more than a thought experiment, by the way. There are research programs actively looking for it on Earth. Felisa Wolf-Simon famously claimed in 2010 to have found a bacterium that could substitute arsenic for phosphorus in its DNA, a finding that would have implied a fundamentally different biochemistry. The result was eventually overturned, but it produced a small flurry of new searches for organisms whose biology might be sufficiently different from ours that we have been overlooking them. None of those searches has, so far, produced a confirmed shadow lineage. The search continues, but if the shadow biosphere exists, it is hiding well even from people trying very hard to find it on a planet they live on. The Habitable Worlds Observatory is supposed to push past this. HWO, as I mentioned earlier, is the proposed NASA flagship for the 2040s. It is currently in the technology selection phase, with a slate of industry contracts announced on January 5, 2026. The mission, if it flies, will use a starshade or a coronagraph to block out the parent star and directly image at least 25 Earth-like planets in the habitable zones of nearby Sun-like stars. Direct imaging would give much cleaner spectra than transit spectroscopy can. The expected cost is north of $11 billion. The expected launch is in the early to mid-2040s. Even HWO will not solve the biosignature ambiguity. It will narrow it. It will give us better signal to noise. It will image planets we have never been able to see at all. But it will not change the fact that the chemistry of biosignatures is irreducibly hard. There is no chemistry that says biology with absolute certainty from 100 light-years away. The molecules we are looking for can be made in other ways. The patterns we are looking for can be produced by other processes. The gap here is not a gap of better instruments. The gap is built into chemistry itself. This is the cleanest expression of the central thread of tonight. We can find chemicals that look like life. We may never be able to prove they were made by life. The distance between possibility and proof in this domain is permanent. It is the difference between observing a pattern and explaining it. And explanation, for atmospheres on distant worlds, requires assumptions we cannot fully test. So we will keep collecting suggestive data. K218b will be joined by 10 more worlds with maybe DMS signatures, then 100. The probability that some of them are real, taken together, will rise. The certainty about any single one of them will not. There is a quiet philosophical move buried inside this last paragraph that is worth surfacing. We are, in this scenario, gathering statistical evidence about the existence of life in the universe without ever confirming a single specific instance. That is not how detection has historically worked. Historically, you found one example, established it beyond doubt, and then started looking for more. Atmospheric biosignature science may invert that. We may build up the case for life through an accumulation of probable detections, none of which is individually conclusive, until the working assumption in the field becomes, of course, life is widespread. That is a kind of detection, but it is not the kind anyone was originally asking for. And it is worth asking, as we get closer to that situation, whether we will accept it as an answer is less than break time equals 1s, is greater than number. Part 7. The Architecture of Listening. If the atmospheric frontier looks like an exhausting argument about chemistry, the signal frontier looks like an exhausting argument about engineering. We have been listening for technosignatures for 65 years. We have built bigger dishes, better receivers, faster computers, the amount of sky we can scan in a year, the number of frequencies we can scan at once, the sensitivity of our detection algorithms. All of these have improved by orders of magnitude since Drake's Project Ozma, and we have found nothing. Or, more precisely, we have found a long series of candidates that turned out to be something else. The pattern. Again, let me explain the intuition behind Radio SETI, because it is worth understanding why we look at radio in particular, why we look at the frequencies we do, and what we expect a technosignature to look like. Natural radio sources in the universe, pulsars, quasars, supernova remnants, the cosmic microwave background, produce what we call broadband emission. Their energy is spread across a wide range of frequencies. If you plotted the strength of the signal against frequency, you would see a smooth curve, sometimes with a slow tilt, but not with sharp, narrow peaks. Nature, in other words, paints with a wide brush. A technological signal is different. Anything we build that produces a deliberate radio signal, a radio station, a cell tower, a military radar, a satellite uplink, concentrates almost all of its energy into a very narrow band of frequencies. typically less than 1 Hz wide. The reason is efficiency. If you are trying to communicate information, you want to put all your power into a tiny range so the receiver can pick it out cleanly from the noise. A natural process has no reason to do this. A technology has every reason to. There is an additional layer to this argument that is worth pulling out. Even if a civilization is not deliberately broadcasting, their incidental radio emissions, the leakage from radar, from communications networks, from internal power systems, would naturally concentrate energy into specific narrow bands. Our own civilization produces this kind of leakage by the trillions of watts. Our military radars, our television transmitters during the era when television was broadcast over the air, our cell tower infrastructure, all of these leak signals into space at frequencies that natural sources do not produce. A sufficiently sensitive observer somewhere in our galaxy could, in principle, see Earth as a planet that lights up at certain narrowband frequencies it has no business producing. We are, in this technical sense, already a beacon. We have been one since at least the 1940s. SETI is, in part, betting that there are other planets in similar states. So narrowband signals are, at least in principle, the cleanest signature of intelligence we know how to look for. If you see a signal that is a fraction of a hertz wide, sustained for any meaningful length of time, coming from outside the solar system, it almost certainly was not made by a star. It was made by a transmitter. The places where this listening happens are scattered across the planet now. The Allen Telescope Array in Northern California was completed in 2007 with private funding from Microsoft co-founder Paul Allen. It is 42 6-meter dishes, working together as a single instrument. It is one of the few observatories built specifically and primarily for SETI. The Greenbank Telescope in West Virginia is a 100-meter steerable dish, the largest fully steerable telescope on the planet. It sits inside a region called the National Radio Quiet Zone, where federal regulations restrict the use of radio transmitters to protect astronomical observations. Even the local sheriff's deputies use specially modified radios when they patrol the area. The Meerkat Array in South Africa, 64 dishes, came online in 2018. It is the precursor to the Square Kilometre Array, which when completed will be the most sensitive radio observatory ever built. The largest current SETI program is Breakthrough Listen, founded in 2015 by the billionaire Yuri Milner, with an initial commitment of $100 million over 10 years. Breakthrough Listen surveys about 1 million nearby stars, plus the central region of the Milky Way and several nearby galaxies, across frequencies from 1 to 12 gigahertz. The program processes about 150 terabytes of data per night, at peak observing. Its pipelines are automated, but every interesting candidate is reviewed by a human analyst. The shape of the search, in practice, is built around 3 filters. The first is drift rate. A signal coming from a planet orbiting another star will not stay at a single frequency. As the planet rotates on its axis and orbits its star, the Doppler shift between the planet and us changes slowly, smoothly. A true technosignature would drift across frequency in a way that exactly matches what you would expect from an orbiting source. A signal that does not drift at all, or that drifts oddly, is almost certainly local. A satellite, a piece of ground equipment, a microwave oven. The second filter is persistence. A signal that appears for 30 seconds and then disappears could be anything: a transient piece of interference, a brief atmospheric phenomenon, an electronic glitch. A signal that you can confirm with a second observation, ideally from a different telescope, is much more likely to be real. The third filter is location lock. A real signal stays associated with the same patch of sky. If you point the telescope away from the candidate target and the signal disappears, that is a good sign. If you point it back and the signal returns, even better. Many candidates fail this test almost immediately. Some fail it the moment a second observation is attempted. Some fail it after weeks of follow-up. Some, like BLC-1, take more than a year of careful work to walk back. The triage is brutal. Most of the signals that come out of the automated pipelines are dismissed within minutes. The ones that survive minutes are often dismissed within days. The ones that survive days enter a different category, and the team's pace slows down dramatically. The closer to the front of the funnel a signal sits, the more skeptical the human reviewers become, because they know how many ways the data can deceive them. The data volume is the thing that has changed most in modern SETI. Drake's Project Ozma scanned a single channel at a time. The Big Ear, where the WOW signal was detected, scanned about 50 channels at once. Breakthrough Listen, at full operation, scans tens of billions of channels simultaneously. The sheer number of frequencies being observed every second means that if a signal is out there, the program will see it. The other thing worth noting about modern SETI is how small a fraction of the searchable universe it has actually canvassed. By some careful estimates, the total volume of stellar space that SETI has examined, at adequate sensitivity, across all the frequencies a technology might use, amounts to something like dipping a single drinking glass into the entire Pacific Ocean and reporting that there are no fish. The Pacific is full of fish. The drinking glass simply has not sampled them. This is part of why the long silence is not, by itself, strong evidence that no one is broadcasting. It might just mean we have not looked in the right place at the right time on the right frequency. The sample, against the size of the question, is very small. And yet, after 65 years, after billions of dollars of effort across multiple generations of equipment, after dozens of programs around the world, the answer is the same as it was in 1960. Nothing, or, more precisely, a long succession of nothings, each of which momentarily seemed like something. The next part is about those candidates, the moments when we thought, briefly, that we had crossed the gap, and what we learned when we walked them back. Is less than break time equals 1s? Is greater than? Number. Part 8. The candidates that turn to dust. The most recent serious SETI candidate, before the 3I, Atlas observations, was something called BLC-1. The initials stand for Breakthrough Listen Candidate 1. It was the first signal in the Breakthrough Listen program, after years of operation, to survive enough of the automated filters to be reviewed by humans. The story begins on the 29th of April, 2019. The Parkes Observatory in New South Wales, Australia, a 64-metre dish made famous in part by its role in receiving the Apollo 11 moon landing broadcast, was observing Proxima Centauri as part of a 30-hour Breakthrough Listen campaign. Proxima Centauri is the closest star to the Sun, 4.24 light-years away. It has at least 2 known planets, one of which sits in the habitable zone. If a technosignature is out there to find, Proxima would be a natural place for it to be. During the observation, the receivers at Parkes recorded a narrowband signal at 982.002 MHz. The signal lasted 30 hours. It had the right frequency stability. It drifted in the way you would expect from a source on a rotating planet. It was located by every test the team could run in the direction of Proxima Centauri. For about 18 months, BLC-1 was treated as the most promising candidate in the history of SETI. The team kept the result quiet while they ran follow-up tests. By the time the story broke in late 2020, the careful work had already begun. In October 2021, a series of detailed analyses, led by graduate student Sophia Sheikh and her colleagues, was published in Nature Astronomy. The conclusion was difficult. BLC-1 had lookalike signals. The team had searched the same frequency range across the rest of the observation campaign when the telescope was pointed elsewhere, and found multiple signals with similar properties: drift rates, durations, narrowness, These lookalikes were clearly produced by human technology on Earth. They were forms of radio frequency interference, leaking through the receiver in ways that made them appear to come from the direction the telescope was pointed. BLC-1 was, almost certainly, one of those lookalikes. The reason it looked so much like a real signal is that human-made radio equipment is now ubiquitous enough that we can produce, by accident, signals with most of the properties we associate with technological origin. The very thing we expect a real technosignature to look like, our own technology produces all the time. The Ross 128 incident, 3 years earlier, taught a similar lesson. On the 12th of May, 2017, Arecibo Observatory in Puerto Rico picked up a strange, repeating, wideband signal in the direction of Ross 128, a red dwarf 11 light-years away. The signal had unusual properties. It was bursty, repetitive, and not obviously consistent with any known natural source. Word leaked to the press almost immediately. For a few days in mid-July of that year, aliens at Ross 128 was a global news story. The team at Arecibo, joined by colleagues at the Allen Telescope Array and at the Green Bank Telescope, ran careful follow-up observations within 2 weeks. They concluded that the signal was almost certainly produced by one or more geostationary satellites that happened to be in the line of sight to Ross 128 during the original observation. Satellite signals can be reflected, refracted, and Doppler shifted in ways that mimic celestial sources. The Ross 128 story died as quickly as it had appeared. But the most beautifully embarrassing example of all is the peritons at Parkes. From 2007 onward, the Parkes Observatory had been recording mysterious millisecond bursts in its data. The bursts had the dispersion signature of fast radio bursts, which are real astrophysical events from distant galaxies. They were thrown into the same data files as real fast radio bursts. Astronomers analyzed them, wrote papers about them, debated their origin. They lasted only a few milliseconds. They appeared at random times. They were a small mystery, quietly accumulating in the literature. In 2015, an Australian PhD student named Emily Petroff and her team finally identified the source. The bursts were not coming from space. They were being produced when someone at the observatory opened the door of the staff microwave oven before the cooking cycle ended. The magnetron in the microwave's interior would continue to discharge for a fraction of a second after the door was opened, releasing a brief pulse of radio energy. The pulse was being picked up by the telescope. One of the persistent small mysteries of radio astronomy was lunch. People had been heating up their leftovers, and Australia's premier observatory had been faithfully recording the radio echoes for nearly a decade. I want to dwell on the peritons for a second, because they capture something important. We tend to think of detection as a clean signal against background problem. The signal is there, or it is not. The data tells you. But the peritons show that even very smart, very careful people can collect strange signals for years and not realize what they are. The data tells you something. It does not always tell you what you think. There is another category of failed candidates worth mentioning because it captures something important about how detection actually unfolds. In 2015, the Kepler Space Telescope noticed unusual brightness fluctuations from a star called KIC 8462-852, more commonly known as Tabby's star, named after the astronomer Tabitha Boyajian, who led the analysis. The star was dimming by as much as 22% at irregular intervals. No known natural process produced light curves like this. For about a year, in 2015 and 2016, Tabby's star was the leading candidate in the world for an alien megastructure. Some researchers seriously proposed that what we were seeing might be a partially complete Dyson sphere, a hypothetical megastructure surrounding the star to capture its energy. The proposal was, By any normal scientific standard, an extraordinary one. But the data was extraordinary, and extraordinary data sometimes drives people to extraordinary explanations. Within 2 years, the data was largely explained. Follow-up observations showed that the dimming was wavelength dependent. Different colors were absorbed by different amounts. A solid megastructure would block all wavelengths equally. The wavelength dependence pointed to dust. Most likely, an irregular cloud of dust orbiting the star is producing the unusual dips. The megastructure hypothesis quietly faded. The papers explaining the dust took longer to write than the original alien speculation did, which is itself a pattern worth noticing. Strange explanations propagate quickly, boring explanations propagate slowly. Both, eventually, get into the literature. The wow signal is now 49 years old. The current best mainstream explanation involves 2 comets, 266 P/Christensen and 335 P/Gibbs, which happened to be passing through the Big Ear's field of view on the night of August 15th, 1977. Hydrogen-saturated gas in the comet's comas, the theory goes, may have produced a brief, narrowband emission at the hydrogen line frequency. The explanation is partially contested. Some of Eamon's original colleagues at Ohio State do not buy it, but it is the leading natural hypothesis. The pattern across all of these stories is the same. We get close, we feel hope, we do follow up. We find an explanation that is, while sometimes mundane, always consistent with what we know about how the universe and our own technology work. The candidate becomes a footnote. The next campaign begins. The gap between detecting a signal and proving it came from intelligence persists. What this teaches us, more than anything, is patience. The next candidate will come. It will be exciting. It will run for a few months or a few years. And then, very probably, it will be explained. The detection of alien life through radio, if it ever happens, will probably look like the wow signal, except for one feature. It will repeat. A real technosignature, unlike everything we have seen so far, will appear again when we point our telescopes back at the same patch of sky. The repeat is the test. We are still waiting for one to pass it. Is less than break time equals 1s, is greater than number, part 9.3, I, Atlas, and the third visitor. On the 1st of July, 2025, a small telescope in Chile, part of an asteroid tracking network called the Asteroid Terrestrial Impact Last Alert System, picked up a new object moving through the solar system. Within hours, the orbit was provisional. Within days, it was confirmed. The object was on a hyperbolic trajectory. Its speed and direction were such that it could not be bound to the sun's gravity. It had come from interstellar space. It was given the designation 3I, Atlas. The 3I means it is the third interstellar object ever observed. The first was Oumuamua in 2017, a cigar-shaped object that produced a small global controversy when Harvard astronomer Avi Loeb argued it might be an alien light sail. The second was 2I Borisov in 2019, which turned out to be a fairly conventional comet from beyond the solar system. 3I, Atlas, is the third, and in some ways the strangest of the three. The strangeness begins with the chemistry. As 3I, Atlas approached the inner solar system in the autumn of 2025. Telescopes around the world measured the composition of its coma, the cloud of gas and dust that surrounds a comet as the sun heats it. The deuterium to hydrogen ratio in the water vapor was extraordinary. Deuterium is a heavy form of hydrogen with an extra neutron in its nucleus. In normal solar system comets, deuterium is present at about 1 part in 10,000 of the total hydrogen. In 3I, Atlas, the ratio was up to 1 part in 100, 100 to 1,000 times higher than expected. The carbon-12 to carbon-13 ratio was also unusual. Most solar system bodies have carbon ratios close to 90 to 1. 3I, Atlas, measured significantly different, suggesting it formed in a chemically different environment. The molecule cyanogen, Cn, appeared in unusual abundance. Most strikingly, polarimetric measurements, observations of how light from the comet is polarized as it scatters off dust particles, showed extreme negative polarization. The result was reported in a paper at RZEV reference 2509.05181 in September 2025. None of these measurements, taken alone, was evidence of intelligence. All of them, taken together, told us that 3I Atlas was assembled from materials that came from a region of the galaxy chemically different from anything we have direct access to. It was a sample, of sorts, of a different stellar system drifting through our own. As the comet approached its closest passage to Earth on the 18th of December of 2025, the Breakthrough Listen team organized a coordinated technosignature search. The Green Bank telescope was reserved. The Meerkat array in South Africa was reserved. The plan was simple. They would scan the object across the radio frequencies, most likely to carry an intelligible signal from 1 to 12 gigahertz, during the period when it was closest and most observable. The result, announced in early 2026, was the same result SETI has been announcing for 65 years. No credible narrowband radio technosignatures detected. Meerkat did pick up hydroxyl emission consistent with cometary outgassing water vapor breaking apart in sunlight and producing a natural radio signal in the hydrogen-bonded radicals. That was the only thing we heard from 3I, Atlas, the sound of ice turning into vapor. Avi Loeb, who had been on the edge of this story since Oumuamua in 2017, published a series of analyses arguing that the deuterium ratio was suspicious. Loeb's argument runs like this. Deuterium is the ideal fuel for nuclear fusion. The hardest fusion reaction to ignite, the one that powers our hydrogen bombs, and that is the basis for nearly every conceivable fusion engine design, is the fusion of deuterium with another heavy hydrogen isotope, tritium, or with itself. If a civilization had ever built a deuterium-burning fusion engine, the exhaust of that engine, the unreacted fuel, the trace residues, would naturally produce a chemical signature exactly like the one we measured in 3I Atlas. High deuterium to hydrogen ratio, water and methane both enriched. Loeb has placed 3I Atlas at level 4 on a scale he himself proposed, called the Loeb scale, which ranges from 0 definitely natural to 10 definitely artificial. He is careful to say that level 4 does not mean the object is artificial. It means the object has anomalous features that are worth taking seriously. The mainstream scientific reaction has been firm. The deuterium enrichment, multiple papers have argued, can be explained by the conditions under which 3I Atlas formed. Deuterium fractionation is sensitive to temperature. In very cold molecular clouds, colder than the protoplanetary disk, our solar system, formed in water, can become significantly enriched in deuterium through normal chemical processes. The unusual carbon ratios can be explained by chemistry in the same cold environment. The negative polarization is unusual, but not impossible. The mainstream view is that 3I, Atlas, is an unusual but natural comet formed in a colder, chemically different region than our own protoplanetary disk produced. To give you a sense of how exotic this comet's origin probably is, the deuterium ratios we measured are most consistent with formation in molecular clouds at temperatures below 20 Kelvin colder than the coldest regions of our own protoplanetary disk. Whatever stellar system birthed 3I, Atlas, the chemistry of its outer regions was running at a different temperature than the chemistry that built our solar system. That alone is a remarkable scientific result. We have, in effect, received a sample from a different chemical environment, and we have analyzed it in real time as it passed. Before 2017, no one had ever observed an interstellar object up close. Now we have observed 3. The third has chemistry we have not seen before. The pace of discovery in this small subfield is accelerating, and the next interstellar visitor, there will be one, probably within the decade, will be analyzed with even more careful instruments. We may find that anomalous chemistry is not anomalous at all. We may find that it is the norm, and that our own solar system is the odd one out. That possibility, in itself, is humbling. We tend to assume our solar system is typical. The growing exoplanet catalogue has already been chipping away at that assumption for 30 years. Most exoplanetary systems we have found do not look like ours. The interstellar comet measurements may be pulling our entire frame of reference further outward. But, and this is the part that matters for tonight, even with all the telescopes, all the radio dishes, all the chemical measurements, all the months of observation, we walked away unsure. 3I. Atlas is now racing back into interstellar space. By the time you hear this, it is already beyond the orbit of Mars. By 2030, it will be too far away to study in any meaningful detail. By 2050, it will be effectively gone. We will never see this object again. The book on 3I, Atlas, is now permanently half open. And it will stay half open because the data we collected does not resolve to certainty. We have a strange comet. We have someone respectable insisting it might be a fusion exhaust trail. We have most of the field disagreeing. We have, in other words, the same thing we have at K218b, a signal that hovers, an interpretation that does not converge. This is the lived experience of the detection problem at every scale. From a planet 100 light-years away, from an interstellar object that passed within 20 million miles of our own planet, from radio surveys of the entire nearby galaxy, the result is the same. Something is happening. We cannot tell you what. There is something specifically painful about the 3I, Atlas case that does not apply to most of the other detection failures we have walked through. With K218b, we can keep observing. The planet is there. JWST is there. New data will accumulate. With Breakthrough Listen, we can keep listening. The galaxy is there. The dishes are there. New campaigns will run. But 3I, Atlas, is gone. The closest approach is past. The chemistry is past. The window in which any further measurement is possible is closing rapidly. We will never get another look at this particular object. Whatever was true about its origin is now permanently filed under We Do Not Know. It is the only one of the major recent detection puzzles that has, in this practical sense, run out of time. There is one obvious response to this pattern, which is that we should stop trying to detect aliens at a distance and start looking up close. We should go to a world in our own solar system where life is plausible, dig in, and see what we find. That is the topic of the next act. Is less than break time equals 1s is greater than number part 10, closer to home, Mars, Europa, Enceladus. The pivot in tonight's argument is the most natural one in astrobiology. If detection at a distance is so fraught, why not go and look up close? Why not pick a world in our own solar system where life is plausible, send a spacecraft, and put the answer beyond doubt? The pivot sounds reasonable. The reality is more complicated. The proximity does not close the gap. It just changes the shape of the gap. Let me show you what I mean. Mars first. Perseverance landed in Jezero crater on the 18th of February, 2021. Jezero, several billion years ago, was a crater lake fed by a river system. There is a clear delta on its western edge. There are layered sedimentary rocks. There are mineral deposits that, on Earth, are associated with microbial activity. The rover's job, among other things, is to identify samples that might preserve biosignatures from the early Martian biosphere, if such a thing ever existed, and to cache them for return to Earth. In September of 2024, Perseverance drilled into a rock named Chayava Falls after a waterfall in the Grand Canyon. The rock was reddish, layered, and ordinary-looking on the surface. The Pixel instrument, the planetary instrument for X-ray lithochemistry, revealed something extraordinary inside. The rock contained leopard spot textures, with iron-bearing and phosphate-bearing veins running through it, and concentrated regions of organic carbon distributed in patterns that, on Earth, are usually associated with microbial activity in ancient sediments. The Sherlock instrument, which measures Raman spectroscopy of organic molecules, confirmed the carbon was bound up in complex compounds. This is the strongest in situ biosignature candidate ever discovered on another world. The patterns at Chayava Falls are not, by themselves, proof of past Martian life. There are non-biological explanations, including certain kinds of mineral precipitation reactions. But the combination of organic carbon, the right mineralogy, and the right textural patterns all in the same rock, in the same place, is exactly what we would expect from a fossilized microbial community. The Chayava Falls sample is now sealed in a small titanium tube on Perseverance's belly. There is no other rover on Mars capable of retrieving it. The plan, for many years, was Mars Sample Return, a complex multi-agency mission that would have involved a NASA Fetch rover, a NASA Mars Ascent vehicle, and a European Space Agency orbiter, all working together to collect Perseverance's samples and bring them back to Earth in the early 2030s. The cost estimates for Mars Sample Return grew, the timeline slipped. By 2024, the projected cost was over $11 billion, with a return date pushing into the 2040s. On the 8th of January, 2026, a minibus spending package passed by the US House of Representatives effectively zeroed out the program. Mars Sample Return, as a NASA mission, was cancelled. China has now publicly indicated that its planned Tianwen-3 mission, a sample return mission to a different part of Mars, could potentially make a detour to retrieve some of Perseverance's samples in the early 2030s. The European Space Agency is exploring partnerships with India and Japan. The future of the Chayava Falls sample is, at this writing, completely uncertain. It may be the most important rock in the solar system, and we may not bring it home for decades, if ever. Notice what this means for tonight's question. We may have, sitting on the surface of Mars, the most important piece of physical evidence about life beyond Earth that humans have ever obtained, and we cannot get to it. The gap, here, is not a gap of physics. It is a gap of politics, of budget, of priority. The detection problem has, in this case, become a problem of human will. Europa next. NASA's Europa Clipper launched on the 14th of October, 2024. The spacecraft is on a long looping trajectory through the inner solar system. It will fly past Mars for a gravity assist, then past Earth for a second gravity assist, then arrive at Jupiter in April of 2030. It will not orbit Europa. Jupiter's radiation environment is too brutal for that. Instead, the Clipper will orbit Jupiter on a highly elliptical path, dipping in for 49 close flybys of Europa over a 4-year mission. Europa itself is one of the most interesting worlds in the solar system. It is a little smaller than our Moon. It has an icy shell estimated at between 16 and 30 kilometers thick. Beneath the shell, the gravitational tides from Jupiter and the other major moons heat the interior, and an ocean of liquid salt water exists in contact with a rocky seafloor. The ocean is between 60 and 100 kilometers thick from top to bottom. It contains more liquid water than all of Earth's oceans combined. The Clipper carries a payload of 9 science instruments. The one most relevant to tonight's question is called SUDA, the Surface Dust Analyzer. SUDA is a mass spectrometer designed to analyze the chemistry of microscopic ice grains that strike the spacecraft during each Europa flyby. Europa, like Enceladus, vents plumes of water and ice into space from cracks in its surface. The clipper will fly through some of these plumes. A paper in the journal Science Advances in 2024 by a team led by Fabian Klenner at the University of Washington demonstrated something remarkable. The team showed that SUDA, in laboratory tests, can identify the chemical signatures of a single bacterial cell embedded in a single ice grain, even at the 4 to 6 kilometers per second impact speeds that occur during a Europa flyby. If there are microbes in Europa's plumes, and if those microbes contain the kinds of biomolecules our own life contains, the clipper has a chance of finding them. In January 2026, JWST and the Very Large Telescope in Chile published new observations of Europa that detected ammonia signatures in or near the Moon's surface. Ammonia is interesting for several reasons. It can serve as a nutrient for certain kinds of microbial life. It acts as an antifreeze, lowering the freezing point of water and helping to keep subsurface oceans liquid at lower temperatures than pure water would allow. The detection of ammonia at Europa raises the habitability case considerably. Notice the structure of this story, though, which mirrors everything we have already discussed. We will not be on the surface of Europa. We will not even orbit it. We will fly past it very fast, 49 times. If the plumes happen to be active during a flyby, if the plumes happen to come from places we fly through, if the cells, if there are cells, happen to be in the grains we hit. Even with the best mission, the answer Europa gives us may be ambiguous. We may detect something. We will probably detect something. Whether what we detect is biological will be the K2, 1,8b argument all over again, just with different chemistry. And then there is Enceladus, Saturn's small, icy moon, just over 500 kilometers across smaller than the British Isles. Saturn's gravity tides keep Enceladus warm enough to maintain a subsurface ocean of liquid salt water. Through long cracks at its south pole, called tiger stripes, Enceladus vents enormous plumes of water vapor and ice grains into space. The plumes were discovered by the Cassini spacecraft in 2005. Cassini flew through these plumes 3 times in 2005, 2008, and 2009 and sampled them directly with its mass spectrometers. The Cassini results told us that Enceladus's ocean contains salts, complex organic molecules, molecular hydrogen, and likely hydrothermal activity at its rocky seafloor. The list of ingredients for life, by any reasonable definition, is largely present at Enceladus. In early 2026, a collaboration between researchers in Japan and Germany recreated the chemistry of Enceladus's ocean in the laboratory using updated data from Cassini. They mixed water with the trace minerals expected from Enceladus's likely rocky seafloor, applied the temperatures and pressures expected at the bottom of the ocean, and added dissolved hydrogen. The chemistry produced amino acids, the building blocks of proteins. It produced aldehydes and nitriles. It produced glycine, the simplest amino acid, in measurable quantities. The full set of organic compounds that emerged is essentially the starter pack for life on Earth. This does not mean Enceladus has life. It means the chemistry is right. The building blocks are made for free, given the conditions present. Whether anything has assembled those building blocks into something living, we do not know. The strange thing about Enceladus, from a detection perspective, is that the Moon is essentially handing us samples of its interior for free. Most worlds in the solar system hide their oceans under crust. To sample those interiors, you need to drill. Drilling on another world is one of the hardest engineering problems humans have ever proposed. Enceladus skips the drilling entirely. The Moon vents its ocean into space, where any passing spacecraft can fly through and sample directly. The only thing standing between us and a definitive answer about life on Enceladus is the cost of building the right instrument and flying it there. There is a proposed mission called the Enceladus Orbilander that would orbit Saturn, sample Enceladus's plumes multiple times, and then land on the surface near the tiger stripes for direct analysis. The mission has been ranked highly in the most recent Planetary Science Decadal Survey. It has not been funded. Like Mars sample return, it is at the mercy of priorities that fluctuate with each U.S. budget cycle. The pattern in our solar system search now mirrors the pattern in the exoplanet search. We have one extremely strong biosignature candidate, Cheava Falls on Mars, that we cannot retrieve. We have one promising target, Europa, that we are slowly approaching. We have one chemically welcoming world, Enceladus, that we have not been back to since Cassini's mission ended in 2017. The gap remains, even in our own solar system, even with rovers and orbiters and direct chemistry. The gap between possibility and proof is still measured in decades, in billions of dollars, in acts of political will. The proximity does not close it just changes its shape. Is less than break time equals 1s? Is greater than. Number, Part 11. The Fringes, what mainstream science avoids. If we widen the lens a little, beyond the careful, hedged, peer-reviewed search programs, there is a whole territory of ideas about alien life that mainstream science treats with caution and that the wider culture treats with intense interest. I want to walk through some of those ideas because they bear on tonight's question even when they sit outside the journals. I will flag clearly what is speculative, what is unverified, and what is taken seriously by serious researchers. Not all of these ideas are equal. None of them are settled. Begin with directed panspermia. The hypothesis was proposed in 1973 by two of the most respected biochemists of the 20th century, Francis Crick and Leslie Orgel. Crick had won the Nobel Prize in 1962 for co-discovering the structure of DNA. Orgel was a leading researcher on the chemistry of the origin of life. They published a paper in the journal Icarus arguing that the building blocks of life on Earth might have been deliberately seeded here billions of years ago by an earlier civilization, perhaps using microbial spores shielded inside small unmanned probes. The evidence Crick and Orgel cited at the time was thin but provocative. The universality of molybdenum in certain critical biological enzymes, despite molybdenum being a fairly rare element on Earth, was one of their starting points. The apparent speed with which life appeared on Earth, once the planet cooled within a few 100 million years, possibly less, was another. The absence, at that time, of any obvious purely chemical pathway from non-life to life was a third. Modern origin of life research has produced much better candidate pathways since 1973, and the directed panspermia hypothesis has fallen out of mainstream favor. But it has never been disproven. It is a theory we cannot, in principle, test. If life was seeded here by an earlier civilization, the seeds would now be indistinguishable from native life, because every cell in your body would be the descendant of the seed. There is no straightforward way to detect that history. The zoo hypothesis is another idea that lives outside the journals. It was first formally articulated by John Ball, an MIT radio astronomer, in 1973. The idea is simple. The galaxy may be full of civilizations. Earth has been deliberately left alone, treated as a kind of cosmic wildlife preserve, observed but not contacted, until we reach some unspecified maturity threshold. Maybe when we develop faster than light travel. Maybe when we stop fighting wars. Maybe when we ask the right question. The zoo hypothesis explains the great silence elegantly, but it does so at a cost. The hypothesis is essentially untestable. If the zookeepers are good at their jobs, we will never see them until they decide we are ready. The dark forest idea is more recent in the popular imagination, though its roots are older. It was articulated most famously by the novelist Liu Cixin in his three-body problem trilogy beginning in 2006. The idea is that civilizations are silent because broadcasting is dangerous. Once another civilization knows you exist, the rational move in a universe of limited resources and uncertain intentions may be to destroy you preemptively, so everyone stays quiet. The galaxy is full. It is also full of predators. The smart move is silence. The dark forest hypothesis has a game-theoretic logic that is hard to dismiss entirely. There are real papers in the SETI literature exploring versions of this argument. If it is correct, then our own behavior, the Arecibo message, the Voyager records, every radio leak from every television broadcast since the 1930s has been an act of cosmic recklessness. The planetarium hypothesis, proposed by the British science fiction writer Stephen Baxter, is stranger still. The idea is that the universe outside Earth's immediate vicinity is a high-fidelity simulation maintained by an external intelligence for purposes we cannot fathom. We see stars and galaxies, but they are not there in the conventional sense. The simulation simply produces the appropriate light when we look. The planetarium hypothesis is, like the zoo hypothesis, essentially untestable. It is also philosophically uncomfortable in ways most working scientists prefer not to engage with. I mention it not because it is likely, but because it is one of the only frameworks that fully accounts for why detection might be permanently impossible. If there is nothing out there, detection is not difficult. It is undefined. And then there is the UFO question. The cultural energy around UFOs, or as the US government now prefers to call them, UAPs, unidentified anomalous phenomena, has changed substantially in the last several years. In July 2023, the U.S. Congress held public hearings in which a former Air Force intelligence officer named David Grush testified under oath that the U.S. government has retrieved what he called non-human biologics from crashed craft. The Pentagon's All-Domain Anomaly Resolution Office, AARO, established in 2022, has investigated over 1,000 cases since its founding. Most cases have been explained as conventional aircraft, balloons, drones, or optical illusions. A small fraction by AARO's own published reports, roughly 2 to 4%, remain unexplained. A careful note is required here. Unexplained is not the same as alien. The history of every major SETI candidate I have already walked through teaches us that we cannot yet identify this, is not evidence of anything in particular. It is the absence of an identification. The Pentagon's unexplained cases may, over time, be resolved into balloons, drones, conventional aircraft observed at strange angles, or atmospheric phenomena. Some may remain genuinely puzzling without being extraterrestrial, but here is the thing. The cultural pressure to interpret unknowns as alien visible in K218b headlines, in 3i, Atlas coverage, in the AARO hearings, in every YouTube video that uses the phrase "scientists are baffled" is itself part of the detection question. We are a species that wants very badly to find the answer. We have been waiting for 65 years. We are getting tired of the gap. When data is ambiguous, the imagination rushes in. What rushes in tells us more about ourselves than it does about anything beyond Earth. There is a useful framing for these unexplained cases that comes from epistemology rather than astronomy. A signal is not evidence by itself. A signal becomes evidence only in the context of a hypothesis it is supposed to support. The same unexplained light in the sky can be evidence for an alien craft, evidence for a classified military project, evidence for an atmospheric refraction event, or evidence for nothing in particular. Which of these things it is evidence for depends entirely on which prior framework you bring to it. The cultural battle over unidentified phenomena is, in large part, a battle over which framework is the default one. There is no neutral position. Every interpretation already carries an embedded view of what the world is likely to contain. Carl Sagan had a standard for this kind of question that has aged well. Extraordinary claims, he said, require extraordinary evidence. Every claim of detection from K2, 18b, from BLC1, from 3I, Atlas, from Ross 128, from Chayava Falls, from the Pentagon's unexplained cases has fallen short of that bar, some in extraordinary ways. The gap is, in this sense, not a gap of data. It is a gap of standards. To cross it, we will need evidence that closes off every alternative explanation. And that kind of evidence is, by its nature, very hard to produce. The cultural reality, though, is that the question of alien life is no longer confined to scientific journals. It is in Congress. It is on cable news. It is in conversations at dinner tables on every continent. The detection problem has become, in addition to a scientific problem, a sociological one. What counts as proof, when an entire civilization is hoping for an answer, may be different from what counts as proof in a careful laboratory. That is part of what makes this question so difficult, and also part of what makes it so human. The looking is itself a form of self-revelation. The next, and final, part of tonight pulls all of this back together. We have walked through atmospheres, signals, oceans, fringes. We have seen the pattern repeat. We have seen the gap persist. The question now is what to do with what we have learned. Is less than break time equals 1s? Is greater than number. Part 12. Will we ever know? Let me bring the four frontiers together one last time before we end. Atmospheres, K218b, and its contested signal, the Habitable Worlds Observatory, and its 2040-ish promise of imaging 25 potentially habitable exoplanets directly. Signals, Breakthrough Listen, the Allen Telescope Array, Meerkat, 65 years of carefully filtered nothing. Visitors, 3I, Atlas, the third interstellar object racing back into the dark with our questions still attached to it. Oceans, Chayava Falls on Mars, possibly the most important rock in the solar system, stranded. Europa Clipper, on its long arc toward an arrival in 2030, Enceladus, the small moon whose ocean chemistry seems almost designed to make us hope. In every domain, the pattern has been the same. We get close, we see something, we cannot confirm. The closer we get, the more interesting the data becomes, and the more interesting the data becomes, the more carefully we have to interpret it, and the more carefully we have to interpret it, the longer the argument lasts. The gap between possibility and proof persists in every domain we have entered. There is an optimist case for tonight's question, and it is worth taking seriously, because I have spent most of the episode making the case for caution. The optimist case runs like this. The Habitable Worlds Observatory, if it launches on its planned timeline in the early 2040s, will fundamentally change exoplanet biosignature work. Direct imaging is much harder to fool than transit spectroscopy. Imaging 25 potentially habitable worlds will give us enough data points to do statistics. If even 3 of them show oxygen and methane in disequilibrium, the case for biology becomes much harder to dismiss. Breakthrough, Listen, and its successors will by the late 2030s have scanned every star within roughly 100 light-years for technosignatures down to power levels comparable to our own. Combined with the Square Kilometre Array and other next-generation radio telescopes, the sensitivity of our search will improve by a factor of 10 to 100 over the current generation. If anyone is broadcasting in our neighbourhood, we will find them. The Europa Clipper, when it arrives in 2030, will have 4 years of close flybys to work with. If Europa's plumes are active during those flybys, and if the chemistry is what we hope it is, SUDA could potentially detect biomolecules from individual cells. We could have a confirmed in situ biosignature in the outer solar system before 2035. If Mars sample return is somehow revived by China, by ESA, by a private partnership, by a future US administration that reverses the January 2026 cancellation, the Chayava Falls sample could be in laboratories on Earth before the end of the 2030s. The combined analytical power of every astrobiology lab on the planet applied to a single rock with possible biosignatures would be hard for any single ambiguity to survive. In this optimist scenario, the 2040s become the decade when detection finally happens. Multiple frontiers converge. Multiple independent lines of evidence reinforce each other. The question stops being if and becomes how soon. I want to give the optimist case its full weight, because the people working on these projects are, almost without exception, brilliant, careful, and motivated. They are not making promises they cannot keep. They are simply working as hard as they can on a problem that may or may not be solvable in the time frame they have. Hope, in this field, is not naive. It is the engine that funds the work. But there is also the pessimist case, and it is the one I have spent most of tonight making. Every biosignature has known abiotic pathways. Every signal has known terrestrial mimics. Every rock has alternative geological explanations. Even a successful detection at HWO, even a successful narrowband signal at the Allen Telescope Array, even a confirmed biomolecule at Europa would trigger years of debate about whether the result was real, whether the result was biological, whether the result reflected an independent origin of life or a cousin of our own. The shadow biosphere problem, the most uncomfortable version of this, suggests we may have a permanent blind spot. We are calibrated for our own kind of life. If alien life is sufficiently different, our tests may miss it. We could share the galaxy with countless living systems that we cannot recognize as alive. The time problem cuts the other way. The Milky Way is 100,000 light-years across. The age of the galaxy is over 13 billion years. Civilizations could have arisen, flourished, and vanished in tens of thousands of years and left no trace. We may be detecting the silence of a galaxy that was once full, in eras we will never see. Or we may be in a quiet window, alone in a particular epoch when most worlds are between extinctions. And there is a final pessimist case that is harder to articulate because it shades into philosophy. It is that detection of another mind may require something more than instruments. It may require proximity, presence, an act of contact rather than an act of observation. Maybe the universe is structured in a way that hides its other minds from any observer that is not local to them. Maybe distance, in this question, is not just a problem of light years and bandwidth. Maybe it is a problem of what it means to know. The middle case, the one that is probably the most realistic, is something like this. We will spend the rest of this century accumulating probable detections. K218b will be joined by 10 or 20 other worlds with suggestive atmospheric chemistry. Another 3I, Atlas, will pass through and leave us guessing. The Europa Clipper will return ambiguous chemistry from the plumes. Mars will produce another Chayava Falls. Each one will be argued about in journals for years. None of them, individually, will reach the 5 sigma certainty threshold. The cumulative weight of evidence, across many candidates, will probably climb high enough that the working assumption in the field becomes, yes, life is out there. But no single, clean, undeniable detection may ever arrive. Humanity, in this version, will live for the rest of this century in the gap. We will know, in some growing aggregate sense, that we are probably not alone. We will be unable to point at a single specific case and say, that one. We will spend our descendants' inheritance on better telescopes, better probes, better receivers, and the answer will continue to hover at the edge of clarity. That is, in some ways, a strange place to land. It is not the cinematic answer. It is not the moment when the signal arrives and the world changes. It is something quieter and longer, more like an asymptote than an event. And there is a final, more philosophical possibility that this gap is not a temporary feature of our methods, but a permanent feature of being the kind of species we are. Maybe to detect another mind, you would have to be standing next to it. Maybe the universe is set up in a way that the long view always remains uncertain, and only the short view, the local one, the one you can reach with your hands, ever resolves. Maybe distance, in the end, is not just a problem of light years. Maybe it is a problem of what it means to know anything that is far away. Bring it home now. The question of the title, Will We Ever Detect Alien Life?, has a strange property when you sit with it long enough. The longer you sit, the less it sounds like a question with a yes or no answer, and the more it sounds like a description of a condition. The condition of being a young, listening, looking species on a small planet around an ordinary star, in a galaxy we cannot see most of, in a universe we cannot reach the edge of. The condition of asking a question that the universe may not be obliged to answer in our preferred format. Maybe the most honest answer to the question is that we may never produce a single clean detection. Maybe the universe is, for reasons of distance, of chemistry, of time, of epistemology, structured to keep that particular kind of certainty just out of reach. Maybe the gap is the answer. But here is what I want to leave you with. Before you turn out the light, the act of asking is itself the most important thing. The act of pointing a 6.5-meter mirror at the empty space around a red dwarf 124 light-years away and waiting for the photons to arrive. The act of running a 100-meter dish through the same patch of sky for 1,000 hours, listening for a whisper that has not come. The act of throwing 4 spacecraft out of the solar system with diagrams of ourselves on the side, just in case someone finds them in 50,000 years. The act of building, slowly and carefully, the next telescope and the next, knowing that the answer may not come in our lifetimes. That act is what we have. It is what we can be certain of. It is the part of the question that is fully within our power. We are the species that listens. We are the species that builds the equipment and points it at the dark. We are the species that, even after 65 years of nothing definitive, keeps looking up. Whatever else is true about the universe, that is true about us. So maybe the question of whether we will ever detect alien life is, in a way, the wrong question. The right question, the one we can actually answer, is whether we will ever stop trying. And to that question, so far, every generation has given the same response. We will not stop. We will keep listening. We will keep looking. We will keep narrowing the gap, even if the gap is not the kind of thing that fully closes. And in that long, patient, possibly endless act of looking, we may already be doing something that matters more than detection. We may be, slowly and quietly, becoming the species we will have to become if anyone, anywhere, ever does decide to answer back. The looking is the preparation, the patience is the practice, and the night sky, whatever else it contains, is the place where we have already chosen to spend some part of every life that follows ours. Take that with you if you take nothing else away. The patience is the practice. The looking is the answer we already have. Whatever the universe is, whatever it contains, whatever it withholds from us, we are the ones who have decided to keep our eyes open. That decision, repeated across generations, may be the most cosmically significant thing our species has ever done. And we will keep doing it quietly, carefully, hopefully, for as long as we are here to do it. Sleep well.